This is question number 5 on Putnam for year 1985. And if you guys have tried out Putnam questions before, you know they are very, very difficult. So we have a long, windy road ahead of us, but hopefully very rewarding in terms of mathematical problem solving experience and the joy that follows it. So let's read the question. Let I sub m be integral from 0 to 2 pi of cosine of x times cosine of 2x all the way to times cosine of mx, and we wish to find for which integers m between 1 and 10 inclusive is I sub m not equal to 0. So that's giving us a hint that I sub m is indeed equal to 0 for some integers between 1 and 10, and we wish to find where I sub m is not equal to 0. So let's think about this. Let's think about how to change this integral, how to simplify possibly this integral so that we can actually evaluate the value of it. Well, so let's make sure we understand the question first. So when m is equal to 1, so we're looking at this question from m equals to 1 all the way to m equals to 10, and we're only looking at integers, so 1, 2, 3 all the way to 10. When m is equal to 1, we have integral from 0 to 2 pi of cosine of x dx. When m is equal to 2, we have integral from 0 to 2 pi of cosine of x times cosine of 2x dx, and when m is equal to 3, we have integral from 0 to 2 pi of cosine of x times cosine of 2x times cosine of 3x, and so on. And we wish to look at the value of each of this. So what is integral from 0 to 2 pi of cosine of x? Let's just evaluate it for the sake of it. That's 0, because integral from 0 to 2 pi of cosine of x dx, antiderivative of cosine is sine and not cosine, so sine of x, from 0 to 2 pi, and we know sine of 2 pi is 0, sine of 0 is 0, so we know this integral is 0. So this m is equal to 1 does not satisfy our constraint. I sub m is equal to 0 in this case, so that's I sub 1. How about I sub 2? Well, this one is going to take more time to evaluate, and we can try evaluating it for each of them, but obviously I sub 10 is going to take us 10,000 years to figure out if we wish to evaluate them step by step for every single one. So obviously there's some creative way of approaching this problem is going to help us greatly. But we at least understand what to look for. We're looking at these I sub 1, I sub 2 all the way to I sub 10. And I sub 10 is the integral from 0 to 2 pi, and we have cosine of x, cosine of 2x, all the way to cosine of 10x being multiplied together dx. We wish to look at the value for each of them and pick out for which integers. So for this one integer is 1, for this one integer is 2, for this one integer is 10, for which values of m we do not get 0. So 1 does not do the trick, but we are going to see if any of the 2 through 10 is going to evaluate to be not equal to 0. Now, when you encounter a reasonably sophisticated problem, or very sophisticated problem in fact, one of the first steps that you may wish to partake in is the method of experimentation and exploration. Experimentation and exploration. You may want to just mess around with the problem, just try maybe plugging in some interesting values, exploit symmetry, or maybe look at how the function is changing, or maybe try to graph it or visualize it, or maybe represent it numerically. Any experimentation or exploration can shed light on the possible solution, or at least some approach toward the solution, or some approach that does not work. And approach that does not work sometimes reveals more than the approach that works on the nature of the question. Anyways, and that's what we're going to do. So right now we're going to maybe try to evaluate I sub 1, I sub 2, maybe I sub 3 and I sub 4. Let's try to evaluate some of these and see if we can find any pattern, or see how we can, from the first few integrals, infer the value of more complex ones like I sub 10, or in fact I sub 2017. Anyway, since we have a product of lots of cosines, one formula that you may think of is product to sum formula. Product to sum formula. And you may say, why are we even thinking about product to sum? Well, what's easier to evaluate, product of cosines or sum of cosines? So is it easier to evaluate integral of cosine of x cosine of 2x dx, or integral of cosine of x plus cosine of 2x dx? And the answer is the second one by a lot. Second one we can evaluate right away as sine of x plus 1/2 sine of 2x plus c. But the first one is not as clear. We have to do some work with it before we can evaluate it. So sum of cosines is much easier to anti-differentiate than product of cosines. So that's why we're looking at product to sum, because we have products of a bunch of cosines. You may have this formula memorized, but I certainly do not. So let's try to logically think it through and derive it. So we wish to simplify, let's say, cosine of x of 1 times cosine of x of 2 as sum of two cosines, or maybe sum of two sines, who knows. And how can we simplify it? Well, you may see cosine of x1 times cosine of x2 as arising from cosine of x1 plus x2, because cosine of x1 plus x2, this you should have memorized. Cosine of x1 times cosine of x2 minus sine of x1 sine of x2, and we have something very similar to what we want, cosine of x1 cosine of x2. And you may think of how can we get rid of this minus sine of x1 times sine of x2. An easy way is to consider cosine of x1 minus x2, because this one is pretty similar to cosine of x1 plus cosine of x2, except that we have plus sign instead of negative sign right here, and we have sine of x1 sine of x2. So you may say, aha, we can add up these two expressions. We can add up cosine of x1 minus x2 plus cosine of x1 plus x2. Then the sine of x1 and x2 are gonna cancel out, and we're going to have 2 times cosine of x1 times cosine of x2. So we can simply divide by 2 to get cosine of x1 times cosine of x2. So we have just found product to sum formula. Of course, you may have this memorized, especially if you're taking Putnam, but if you do not, it's not very hard to derive it using logical steps. So using this product to sum, let's try to evaluate I sub 2. Let's try to explore and experiment with I sub 2. So we have integral from 0 to 2 pi, and obviously we want to use the product to sum. So we have cosine of 2x times cosine of x. I write it like this since we have x1 minus x2, and just to avoid negative signs. Although it's always good to point out cosine of negative x is equal to cosine of x. So even if we have negative sign, we can just change it to positive right away. Anyway, cosine of 2x times cosine of x, using this formula, we're going to have 1 over 2 right here. And we have cosine of the first thing minus the second thing, in this case 2x minus x is simply x, plus cosine of the first thing plus the second thing, which in this case is cosine of 2x plus x, or 3x dx. And what is the value of this? Well, this thing is 0 once again, because we have 1/2, and we have cosine of x turns to sine of x, cosine of 3x turns to 1/3 sine of 3x from 0 to 2 pi. And sine of 0, sine of 6 pi, sine of 2 pi, all of those are 0, so we get 0. In fact, let's make sure we make this concrete. Cos integral from 0 to 2 pi of cosine of any kx dx, where k is some integer, is going to evaluate to be 0, except one case. And that one case is what's going to shed light on how to approach our entire problem. So let's look at this. Integral from 0 to 2 pi of cosine of kx is always going to be 0, because you're going to get 1 over k sine of kx when you integrate it, and plugging in 2 pi and 0. When you plug in 0, you're going to get 0. When you plug in 2 pi, you have sine of 2 pi k, which is 0 once again. So you're going to get 0 for any values of k, except when k is equal to 0. When k is equal to 0, some interesting thing happens, because we have integral from 0 to 2 pi of cosine of 0, or simply 1 dx. And in this case, we get 2 pi. Let me write this down, because this is so important. This is very, very important. So we know integral from 0 to 2 pi of cosine of kx dx for some k being integer, is equal to 0 if k is not equal to 0, and is equal to 2 pi if k is equal to 0. So the only way integral from 0 to 2 pi of cosine of kx dx is going to be something other than 0 is when you have cosine of 0 or simply 1 inside. And obviously, so we have cosine of x and cosine of 3x, integral from 0 to 2 pi of both of them are going to be 0. So we're going to get 0 for this one. So naturally, you may ask, how are we going to get something other than 0? How are we going to force cosine of 0x to come about inside this integral? So let's experiment just a bit more. Let's look at I sub 3. For I sub 3, we're going to start with I sub 2. So we're going to have 1/2 integral from 0 to 2 pi of cosine of x plus cosine of 3x dx, but we're multiplying by cosine of 3x to the integrand, to inside. So we are multiplying by cosine of 3x to what we used to have in I sub 2. And what is this going to get us? Let's use product to sum one more time. You're going to get 1/2 and 1/2 from both of these. So I'm just going to factor it out to get 1/4. And we're going to have integral from 0 to 2 pi of, you're going to have cosine of 4x plus cosine of 2x from this expression. And you're going to get plus cosine of 6x and plus cosine of 3x minus 3x, or cosine of 0x dx right here, and this thing is 1, of course. And we have something other than 0 for this. You have 0 plus 0 plus 0, and you have integral from 0 to 2 pi being 2 pi for cosine of 0x. So this expression is not going to be 0. So what have we found? I sub 1 does not work. I sub 2 does not work, but I sub 3 does work. It evaluates to something other than 0. This is fascinating. Why don't we explore one more integral just to see? Let's try I sub 4. Obviously, doing this all the way to I sub 10 is going to take a long time because, as you see, the expression inside is doubling each time. For I sub 1, we had one expression. For I sub 2, we had two expressions being added together. And for I sub 3, we have 4 expressions being added together. So for I sub 10, we're going to have 512 equations being added together. And analyzing that may take some time. So anyway, let's try I sub 4. Well, we are going to have another 1/2 getting factored out using product to sum. And we are going to have integral from 0 to 2 pi. And remember, we are multiplying by cosine of 4x to this inside expression. So let's use product to sum one more time. Realize cosine of 4x times cosine of 4x is going to get us what we want right away. We're going to get cosine of 8x and cosine of 0x. So right away, we have something other than 0. So I sub 4 is going to work once again. That's very interesting. So I sub 1 does not work, I sub 2 does not work, I sub 3 does not work, I sub 3 actually works, I sub 4 works, and you can continue this, and it's not hard to see that I sub 5 does not work, I sub 6 does not work, but once you get to I sub 7ish, maybe you're going to have too many expressions to deal with, and one way of actually solving this question is by maybe evaluating it to I sub 6 or I sub 7. That's going to take you some time, but it's not too terrible. And from I sub 7, you can use some logic and you gotta be creative in your explanation. But using some of the things, some of the patterns you see, from I sub 7, you can infer what's going to happen in I sub 8, I sub 9, and I sub 10. And not just the pattern, you can actually prove what happens in I sub 8, I sub 9, I sub 10 just by looking at I sub 7 using the relationship of how these cosines are changing from one term to another. But that's not as formal as we may wish it to be, and I want to explore this question more in depth. So, however, it's very good to point out some of the things that we can see from our exploration. So let's look at it. Let's look at I sub 3 and I sub 4 in particular because they actually turned out to yield a value other than 0. So let's look at this. How did we get cosine of 0x? Because when you have cosine of 0x, you're done. All of these other terms, cosine of 4x, cosine of 2x, and cosine of 6x, is going to turn to be 0 when you integrate it from 0 to 2 pi. Cosine of 0x, having cosine of 0x is the only way you're going to have non-zero value. So let's look at how cosine of 0x came about. So how did we get cosine of 0x? Well, we used to have cosine of x, then we multiply by cosine of 2x, and we got cosine of 3x. So we had cosine of just x But by multiplying by 2x and using product to sum, we got a term with cosine of x plus 2x. And continuing on, we multiply by cosine of 3x, and that got us a term where we subtract 3x, and that's how we got cosine of 0x right here. So now let's look at this cosine of 0x and see how it changed from cosine of x. So we started with cosine of x, and let's make sure we know where this cosine of 0 came from. So we got it from cosine of 4x right here, and cosine of 4x came about when we multiplied by cosine of 3x to cosine of x right here. So we used to have cosine of x, and we changed that, and we subtracted 2x. So you can think of cosine of x as being cosine of x minus 2x, because cosine of negative x is equal to cosine of x. So we have cosine of x, we subtracted 2x, and then from cosine of x minus 2x, we went to this cosine of 4x, or you can think of it as being cosine of negative 4x. So we subtracted 3x, and to go to cosine of 0x, you can think of adding 4x, realize how this thing evaluates to 0. So that's how we got cosine of 0x, by doing x minus 2x minus 3x plus 4x. Maybe now you're seeing a common motif and how we can solve this question. It seems like let me write this down. This assertion is extremely important. It seems like integral from 0 to 2 pi of cosine of x times cosine of 2x all the way to, let's say, cosine of some nx dx is not equal to 0. Not equal to 0 if and only if at least one of the permutations, we're going to count how many permutations soon enough. Permutations 1 plus or minus, 2 plus or minus, 3 plus or minus, all the way to plus or minus n is equal to 0. And of course, I'm talking about some positive integer n. And why? Why am I making this assertion? Well, let's look at cosine of 3x one more time. You have to get cosine of 0x, or you have to get this 0 inside for you to have an integral not evaluating to be 0. And how do we get cosine of 0x? By doing x plus 2x minus 3x. How do we get 6x? By doing x plus 2x plus 3x. How do we get 2x? Well, that's by doing cosine of x minus 2x plus 3x. And how do we get, let me just complete it. How do we get cosine of 4x? That's by doing cosine of x minus 2x minus 3x, which is cosine of negative 4x or cosine of 4x. So realize each of these terms, cosine of 4x, cosine of 2x, cosine of 6x, cosine of 0x, are equal to cosine of x, and you have either plus or minus 2x and either plus or minus 3x. Look at this, cosine of x plus 2x minus 3x, cosine of x plus 2x plus 3x, cosine of x minus 2x plus 3x, cosine of x minus 2x minus 3x. So all of these terms inside can be computed as cosine of x plus or minus 2x plus or minus 3x. And obviously there's 4 choices right here. You have 2 choice for the first sign, you have 2 choice for the second sign. So, and same thing for this one. To get cosine of 0x right here, you have to do cosine of x minus 2x minus 3x plus 4x. So it seems like if we can do, in this case, it was 1 minus 2 minus 3 plus 4. In the case above, you had to do 1 to get 0. We had to do 1 plus 2, if my tablet starts to work, minus 3. So it seems like if 1 plus or minus 2 plus or minus 3 all the way to plus or minus n evaluates to 0, we have this integral not being equal to 0. And if you want to make this more formal, actually let me write this down. Let me write something down just to make sure we understand this statement inside out. So let's consider cosine of x of 1 times cosine of x of 2. Using product to sum, we already know that this thing evaluates to 1/2 times cosine of x of 1 minus x of 2 plus cosine of x of 1 plus x of 2. So now let's try to evaluate cosine of x of 1 times cosine of x of 2 times cosine of x of 3. Well, that's going to be That's going to be, so we're multiplying by cosine of x sub 3 to each of these expressions, and we can use product to sum once again, factor 1/2 out. That's going to get us 1/4 times cosine of x sub 1 minus x sub 2 minus x sub 3 plus cosine of x sub 1 minus x sub 2 plus x sub 3 plus cosine of x sub 1 plus x sub 2 minus x sub 3 plus cosine of x sub 1 plus x sub 2 plus x sub 3. And from this, it's obvious once again how we have, let me actually make this general. So product, so that this capital pi refers to product, just as sigma sign refers to sum. So product from k equals to 1 to n of cosine of x of k. So cosine of x of 1 times cosine of x of 2 all the way to cosine of x of k is equal to cosine of x of n, in fact, because you're doing it to n of them, is equal to 1 over 2 to the what power? We have 1/2, then we have 1/4, then we're going to have 1/8, and so on. If we have 2 elements, we have 2 to the first power. If we have 3 elements, we have 2 to the second power. So having n of them is going to get us 2 to the n minus 1 power. And inside, we have sum of all permutations of cosine of x of 1 plus or minus x of 2 plus or minus all the way to plus or minus x of n. So that's what we have right here. And if you want to write this more mathematically formal, you can write it as 1 over 2 to the n minus 1 power times, you can use the summation sign, and we have x of 1 plus, now we have either plus or minus x sub 2, and you can just write it as, let's say, some coefficient of x sub 2 plus x sub 2 and plus a sub 3 times x sub 3 all the way to plus a sub n x sub n. And of course, each of these coefficients, a sub 2, a sub 3, and all the way to a sub n, can be either 1 or negative 1. So a sub I is equal to plus or minus 1, and we're looking at it for I between 2, so we're looking at it from a sub 2 all the way to a sub n, so I between 2 and n. So let's continue. I'm just trying to make this statement more formal and make sure we understand it inside out and there's no contradictions. So using this, we can say what the expression we have, cosine of x times cosine of 2x all the way to cosine of some nx is equal to 1 over 2 to the, we have n of them, so n minus 1 power, and we have the summation of all of these, summation of sum of all permutations, so sum of all permutations of cosine of x plus or minus 2x plus or minus 3x all the way to plus or minus nx. I'm not going to write the formal sigma for this one. You're welcome to do so. And since we have this, and we also have a very important information that we know, that integral, I wrote this down right here, integral from 0 to 2 pi of cosine of kx is equal to 0 if k is not equal to 0, and it is not equal to 0, it's equal to 2 pi only if k is equal to 0. So we know when you integrate this from 0 to 2 pi, so when you integrate this from 0 to 2 pi dx, you're going to have a bunch of this cosine of x plus or minus 2x all the way to plus or minus nx. You're going to have a bunch of cosine of some kx. You're going to have a bunch of cosine of k sub 1x, cosine of k sub 2x, bunch of these added together. So, and all of these are going to evaluate to be 0, except for the case when you have cosine of 0x inside using what we have seen. So the only way that's going to happen is if the permutations of 1 plus or minus 2 plus or minus 3 all the way to plus or minus n evaluates to be 0. If at least one of them evaluates to be 0, we have what we wish to have. So maybe, hopefully, you now understand this inside out. So we have a much easier question to work with now. We want to find for which positive integers n between 1 and 10 inclusive, 1 plus or minus 2, at least one of these permutations of adding them together evaluates to be 0. And how many permutations are there just for the sake of it? Well, we want, for each of the signs, we have two choices. So we have two choices for this one, two choices for this one. And how many choices do we have? Well, we have n numbers, so you have n minus 1 signs, so you have 2 to the n minus 1 permutations of signs because you have n minus 1 signs and each of them has two choices. Anyway, now let's actually try to examine this from number theoretical point of view. So now let's examine this, 1 plus or minus 2 plus or minus 3, all the way to plus or minus n. One thing you may say is that looking at this question, examining this question and try to infer or maybe try to prove which values of n satisfy this is going to be much easier if we do not have plus or minus. And if we just have 1 plus 2 plus 3 all the way to plus n, if we do not have these pesky negative signs bothering us. And in fact, changing this expression to sum from 1 to n is possible using modular arithmetic. In fact, examining this equation in mod 2 does the trick, because in mod 2, negative 1 is congruent to positive 1 in mod 2. So all of these negatives can be changed to positives. So we have our given statement being congruent to, so this part being congruent to 1 plus 2 plus 3 all the way to plus n in mod 2. And this thing is telling us we have this expression which we can evaluate as n times n plus 1 over 2 being congruent to 0 mod 2 for if the number n satisfy our assertion of this permutation. And what is this telling us? Well, we have n times n plus 1, and when you divide it by 2, we have multiple of 2. N times n plus 1 over 2 is a multiple of 2. That's telling us n times n plus 1 is a multiple of 4. So we know n times n plus 1 is congruent to 0 in mod 4. And from this, we know n is congruent to 0 mod 4, or n plus 1 is congruent to 0 mod 4. You can do this because n and n plus 1, so two consecutive integers, are relatively prime. Since these two are relatively prime, only one of them can be multiple of 4. So we can either say n is congruent to 0 or n plus 1 is congruent to 0. So we know n is congruent to 0 mod 4, or n is congruent to negative 1, which is congruent to 3 mod 4, if it satisfies this assertion. So what have we just figured out? For some n to satisfy this, we know n has to be congruent to 0 or n has to be congruent to 3 mod 4. But we have not proven that it goes the other way. We have not proven that when n is congruent to 0 or 3 in mod 4, that we have our assertion being true, that one of these permutations is equal to 0. What do I mean by that? So let's make sure we understand this, the difference between necessary and sufficient. So let's say you have a square. And you can say something like this: if something is a square, then it is a rectangle. But just because something is a rectangle, so if rectangle, that does not mean it is a square. It does not have to be a square. It is a square. This does not logically follow. And the same applies for us. We know for something to satisfy this, it is necessary for it to congruent to 0 or 3. But just because something is congruent to 0 or 3 does not mean it satisfies it. So now we are going to have to prove this statement the other way. By the way, before I do it, I want to mention something. We have shown that it is necessary for n to be 0 or 3 for it to satisfy the constraint that we wish it to satisfy. And in fact, the solutions that we have found so far at the list of 3 and 4 both satisfy our assertion. 3 is congruent to 3 mod 4, 4 is congruent to 0 mod 4. So far, it seems like what we are trying to prove may work out. So let's make sure we prove the converse. Let's make sure we prove the opposite. So we want to prove So we want to show that when n is congruent to 0 or 3, then we have this expression becoming 0 for some permutation. So we wish to show that this constraint is not only necessary, we have proven the necessary part, but it's also sufficient for one of these permutations to be equal to 0. And doing so is not very hard. We just have to copy off, just extend what we have for I sub 3 and I sub 4. So let's say we have n. Let's say we have n being congruent to 0 mod 4. Then we can set the equation as cosine of x, so that's 1, minus 2, minus 3, plus 4. And we can repeat this many times because n is multiple of 4. You can group this in groups of 4, and we can continue this. 5 minus 6 minus 7 plus 8, so that's equal to 0 once again, and all the way to plus n minus 3 minus n minus 2 minus n minus 1 plus n. So I'm just grouping it because n is a multiple of 4 when it's congruent to 0 mod 4. I'm just grouping it like this, and all of these expressions are going to turn out to be 0. So we have it. We have found some combinations of 1, 2, 3, 4 all the way to n, some permutation of them, I should say, that evaluates to be 0. So n equals to 0 mod 4 is a sufficient condition. How about n being congruent to 3? Well, in that case, we can use what we have right here. So for n being congruent to 3 mod 4, we can say 1, so we did 1 plus 2 minus 3, so 1 plus 2 minus 3. Then we can group things in groups of 4. Then we can do 4, in fact negative 4. One way of doing it is negative 4 plus 5 plus 6 minus 7. Realize that this thing evaluates to be 0. That's 1, that's negative 1. And you can continue this because n is congruent to 3 mod 4. You can continue this groups of 4 all the way, so plus all the way to n minus 3, so negative of n minus 3 plus n minus 2 plus n minus 1 minus n, and all of these expressions are going to turn out to be 0. So we have shown that n being congruent to 3 mod 4 is a sufficient condition, and we have shown that n is congruent to 0 or 3 mod 4 is in fact a necessary and sufficient condition, and we're done. So we have shown that m being congruent to 0 or 3 mod 4 is the answer to this question, and the integers between 1 and 10 that satisfy it is 3, 4, 7, and 8, and we're done.